Okay, welcome everyone. Thank you all for joining this session where we are very lucky to be joined by Scott Chapman from EPS, who will be demystifying zOS CPU measurements for us. Feel free to leave any questions you have in the chat box as we go along the presentation, and Scott will answer them towards the end of the presentation. Also, we'd be grateful if you could leave session feedback as well, and I'll paste in a link in the chat box for that as well shortly. And with that said, over to you, Scott.
All righty, thank you very much. And good morning, good afternoon, good whatever time of the day it is where you guys happen to be. So very happy to be here presenting at the Virtually Unstoppable GSE conference this year. So this is zOS CPU Measurements Demystified. If you don't know who enterprise performance strategies are, we do zOS performance. We do education and consulting. We do our Pivoter performance reporting software as a service, and of course we provide information in forums like this around the world. Just so you know, the performance graphs you see here do come from Pivoter, but you should be able to recreate those in most of the major reporting products, and certainly if you can't, by all means, send us some data. We're happy to do a free cursory review with you. And if you are deficient in that area in terms of performance reporting, note too that we even have a free tier available as well. So just be aware of that. So CPU. CPU measurements can be very confusing. I mean, we throw around terms like MIPS and MSUs and CPU seconds, utilization, service units. And it can be very confusing, especially if you're relatively new in the business, or if you're relatively new even to trying to do zOS performance and capacity, but you've been in the mainframe world for a while. Sometimes trying to understand the relationships of all these terms, it's just a little bit fuzzy, as you see here on the screen. But it's very important to understand those CPU measurements, right? Not the least of the reason why is because the software costs are often predicated either on the CPU capacity or the CPU consumption. And software costs often are the largest part of the mainframe budget. People costs come right in there too, but if you're just looking at the software and the hardware and so forth, software often is much more expensive than hardware. So for that reason, it does make absolute sense to understand CPU. And of course, the CPU capacity and CPU consumption also drives your hardware decisions as well. So understanding the CPU terms is vitally important to anybody who's doing mainframe capacity and performance as well. So we need to understand, how much work can our CPU do, i.e. the CPU capacity, and we need to understand how much of our CPU capacity we're using, i.e. we need to understand CPU consumption. And we also need to understand how both of those are impacting our performance. So in this particular presentation, I'm going to use the term CP and CPU or engine. All of those are meant generically to apply to both specialty engines and general purpose engines. If there's a distinction that matters, I will probably say GCP or GP for general purpose engines, and ZIP for zips or zaps. Zaps are, of course, no longer available as of the Z12s, but we still run across people that have them still every now and then. So in this presentation, we're also going to ignore SMT. SMT is only available for zips, at least within zOS. There's also IFLs, and the SAPs are also run SMT now too. But for this presentation, we're going to ignore SMT because it does not apply to the general purpose engines. And frankly, the general purpose engines are the ones we're most often concerned about because those really drive the software cost, and they're certainly the most expensive capacity to add. So again, we're going to ignore SMT. I have a whole separate presentation on SMT if you really want to understand the SMT measurements. It's on our website. You can go to pivoter.com to get that. Or email me. I'll be happy to talk to you about it. And we're not going to discuss measuring coupling facilities or IFLs. There are some interesting things around that and some of those measurements, but we're not going to talk about that today because we do have limited time. So the primary sources of CPU measurements from the SMF data are the SMF 70, 72, and 30. The 70 gives you basically the LPAR view, the machine view, the overall view at that level. Whereas in the SMF 72, you actually start to see the workload. So down to a service class period basis or a report class basis. And then the SMF 30s are where you can get down to the address space basis. The SMF 30 have several subtypes that are of interest. The end of step records are the subtype 4, the end of jobs are the subtypes 5s. Those are often used for chargeback or application attribution of CPU consumption. Sometimes the interval records, which are subtypes 2 and 3, are also used for chargeback. And in some cases, they're actually more useful for chargeback because instead of waiting for the end of job record to come out, and your job may have crossed multiple days, you get it every SMF interval. So that's the interval records can be even more useful than the end of step and end of job records. If you're doing this sort of analysis, any sort of performance analysis actually in the mainframe, the recommendations is to set RMF or CMF to sync with your SMF interval. Okay, that way you can actually, compare the 72s to the 30s, and you can compare other interval records together to each other. Also, make sure that that interval is no more than 15 minutes. And that they're actually the same across all the systems in your environment. It makes it very difficult to start comparing what's happening on the machine when the machine's recording is at, or the LPAR's recordings are at different intervals. So just be aware of that as well. Okay, so let's start with the most basic definition, which is CPU time. So CPU time is the total time that the CPU has spent executing work for a particular task, okay? So in other words, this is a time, it's an elapsed time, but I hesitate to use the word elapsed time because we often think about the elapsed time, for example, of a batch job, and the elapsed time for a batch job, for example, is going to be much longer than the CPU time because there's other things that happen other than running on the CPU. But the CPU time is the time that the CPU was actually doing work for that particular task who has a CPU time measurement, right? So you could think of it as the time that the workload was dispatched to a CPU. This should probably be amended to say it was dispatched to the CPU and the CPU actually had the CPU, right? So let's ignore the distinction here of, well, zOS dispatched it to the CPU, but LPAR took the CPU away or whatever. The point here is that you're running on the CPU. The task is actually executing on the CPU, and we can measure that duration, okay? And we can measure that duration because the Z architecture has CPU timers that have a nominal resolution of 1 microsecond. Okay, although they're usually not externalized and the SMF data to that level, that is nominally down to the 1 microsecond level. So, and the other important point here about the CPU timers is when the CPU is interrupted to have to go do something else, such as handling an IO interrupt or something like that, the CPU timer is readjusted when the task picks back up and starts executing again. In other words, for a given task, its CPU time is not influenced by, oh, I was dispatched here, I got interrupted to do an IO, I came back. The task CPU time is still accurate for the amount of time that task spent on the CPU. And finally, CPU timers are not dependent upon the time of day clock. So while this is an elapsed duration, this is a time, it's not timed with the time of day clock because the time of day clock, may be steered to stay accurate with UTC. And then, a couple of times a year, we actually jump the time by an hour in many locales, unfortunately. And so these are two good reasons why you don't use time of days timers when you're doing performance analysis, and certainly when the machine is trying to measure CPU time. So this is just an example here of hey, program A comes on the CPU, is running for some period of time, gives up the CPU, program B comes on the CPU, runs for some period of time, gives up the CPU. And you may think, well, why would he give up the CPU? And the answer is, well, when you do an IO or something like that, you have to go into a wait. Maybe he's waiting for a lock. Whatever the reason may be, this program has ended his need for the CPU, right? Here we see program C, program D. You know, think of this on time on the scale of microseconds. So literally these might be, you know, 40, 70, 80, 40. These might be tens of microseconds, right? Things happen very, very quickly down at this level of recording. And you can see here that if we went across the line here, we could say during this time period, program A consumed a total of 90 microseconds, let's say, of CPU time on the CPU, whereas program B consumed 70, here C was 80 and D was 40. Now, despite these very precise CPU timers, if you run the same workload multiple times, you almost certainly will observe variability in the CPU time. Okay, and there's a large number of things that can cause a CPU time variation. Today, probably the most significant one is processor cache contention, because the CPU performance is very dependent upon your L1 and L2 caches, also the L3 and the L4 caches, and that how efficient the particular piece of work is in terms of finding its data in those caches depends in part on what else is running on the system and also putting data in those caches, right? There's also things like locking, serialization, you know, all these other sort of things too that can influence CPU time variability. And that variability can be significant. You know, I say here plus or minus 5%, it's not out of the ordinary. That's kind of a baseline. But even larger variability, plus or minus 10%, is not out of the realm of possibility, especially depending upon how busy the system is, what your configuration is in terms of the LPARs and their logical CPs versus the physicals and all that sort of stuff. So the point down here is that when evaluating before and after performance, it's important to take multiple measurements. If you just do one execution and say, oh, look, my CPU time was 100 seconds, and then you change something and you run it again, you say, oh, look, my CPU time is 102 seconds. That was a negative change. The time went up. That must be bad. That's actually probably well within the range of variation, normal variation. You need to take multiple measurements, try to do an average, throw out the outliers, stuff like that to come to a good conclusion. So hopefully it's clear now that only one task can be dispatched to a CPU at a time. So no more than one task can accumulate CPU time per CPU at any instance, which means the maximum CPU time accumulated per CP is 1 second per second across all LPARs on the machine, okay? This is something that sometimes people have a little bit of trouble understanding, but if you have, for example, a 900-second RMF interval and job A accumulated 450 CPU seconds, and this ran on a machine with 5 active CPs, what portion of the machine, what portion of the CAC did job A consume? Well, if there was 5 CPs on the machine, 5 times 900 means the maximum CPU time that could be consumed across the entire machine during one 900-second interval is 4,500 seconds. So if you take 450 divided into 4,500, that means that that job can consume 10% of the capacity of the machine in that 900-second interval, okay? So how much would it consume if we moved it to a machine whose CPUs were twice as fast? And when we say twice as fast in this context, what we generally mean is they can do twice as much work per unit of time. If we move them to CPUs who can do twice as much work per unit of time, well, then the CPU time will go down because they get more work done per unit of time. And so if we're running on twice as fast CPUs, we'd go down to 225 CPU seconds. Conversely, if we moved them to CPs that were half as fast, then we'd find that the CPU time would go up because the CPUs can get less work done per unit of time, and so we'd go up to 900 seconds. Okay. Now, oftentimes, this can be beneficial, surprisingly, for your overall CPU consumption across the entire machine. Why? Because if you have half as fast processors, you often will have twice as many, right? Because we sell machines, unfortunately, by their overall capacity, and going to more slower CPs is often beneficial for overall efficiency through the system, because you spend less time waiting on CPs, for example, and you get more out of that lovely L1 and L2 cache. So CPU times will change between machines, right? We just talked about what if you move to faster and slower ones, right? But CPU time can also change just based on the generations of machines, the models of the same machines, and even configurations of the same model. So we'd like to approximate those differences so that we can take measurements across different models and compare them. Usually this is an issue if you're changing out your machine and you want to be able to compare the consumption yesterday before the upgrade to today after the upgrade. It'd be nice to be able to normalize that and not just rely on the CPU time. And these are the measurements that we use to try and approximate and normalize consumption across different models or generations. And we're going to talk about each one of those right now. So first up is service units. So service units are intended to translate resource utilization to a value that can be used transparently between machine configurations. And in fact, the WLM policy uses service units to measure resource consumption. So WLM is using service units to measure that resource consumption. We use it in the policies to set durations on service class periods. And that can apply across a sysplex with different machines in it. Now, the actual recorded values are based on the service coefficients defined in the WLM service definition, except when they're not. So most of the time you'll have weighted service units in the records. Occasionally you'll come across a record or a field that has unweighted service units. The recommendation, though, is to set those coefficients for CPU and SRB, which affects the service units consumed on the CPUs, to 1, which means the weighted and the unweighted values are the same. So assuming that you follow that good advice, then you don't really have to worry about the difference between weighted and unweighted service units. So the CPU service units are in fact calculated as the CPU time times the SRM constant times the CPU coefficient. And that SRM constant is recorded in the SMF data. It's available in the control blocks, and you can see it online here. Now, the SRM constant for an LPAR, though, is based on the number of general purpose engines that are online to the LPAR and the machine model. So on a Z05, an LPAR with 3 online general purpose engines gets the SRM constant for a Z03. Now note that's even if one of those 3 engines is parked. So the service units, they do this because they're trying to take into account the MP effect. Historically, this probably made good sense. With hyper dispatch today, it probably makes a little less sense, but nonetheless, it's what actually happens. So this is just an example of that, where a customer actually varied a CPU offline, and you can see that the service units per second constant for the LPAR rose. Okay. This is just an example of some BC12 machines, service units per second constant, and you'll notice that as the number of CPs go up, the service units per second goes down. Just like back here in this chart, when we took a CP offline, the service units per second went up, right? And why is that? Well, again, what they're trying to do is take into account the MP effect, the issue of having multiple CPs sharing cache, and there will be more contention for that cache. There's also the possibility that when a task gets redispatched, maybe it doesn't get redispatched on the same exact CP, and so its data and instructions may not be in the L1 and L2 cache for that particular CP. So that's why this is a per CPU number, and it goes down as you add more CPs. Again, this may not be as accurate as it was in the old days before hyper dispatch, but it's good enough to get things in the right ballpark. And you have to understand all of these measurements that we're talking about to try and compare CPU consumption across different machines is in fact just an approximation. Okay, so even though IBM has these things listed here out to 4 decimal places, don't think that these are that accurate, that, oh yes, we can tell a difference out to 4 decimal places on these service units per second ratings. I actually am kind of annoyed that they take them out to 4 decimal places, because it implies a precision that's really not there, or an accuracy that's really not there. Okay, now the next major one is MSUs, which stands for millions of service units, and really stands for millions of service units per hour, and originally really was take that service units per second constant, multiply it by the number of CPUs, multiply it by 3,600 seconds in an hour. That's a big number, so divide it by a million, and you get something called MSUs. However, and with the 990, the Z990 in 2003, IBM decided that they were going to make software cheaper if you bought a Z990. How did they decide to make software cheaper? They decided to derate the MSU ratings of their machines. So they basically reduced the MSU ratings of its processors about 10% relative to the quote unquote hardware MSU ratings. And this continued through the Z9 and Z10 machines until you got to the Z196, when IBM said, maybe we could actually make software cheaper by making software cheaper. So they actually changed the software pricing metric you could use if you went to Z196, and hence you got a cheaper software that way. So the rated MSUs is no longer directly tied to the service units per second formula up here, but it's very close to this formula down here, which basically derates it relative to what their steps that they took over the years. Now, sometimes people will use the term hardware MSUs versus software MSUs, and if they are making that distinction, they're basically saying hardware MSUs is this thing up here, this is just software MSUs down here. Personally, I don't like to make that distinction, because IBM only provides one MSU rating. The MSU rating is just a relative measure of capacity. Whether that relative measure is scaled by 0.664 or not makes no difference. It's still just a relative scale of capacity. Now, MIPS, the granddaddy. Everybody loves to talk about MIPS, which originally stood for millions of instructions per second. I personally prefer meaningless indicator of processor speed, because it does not mean that you're executing that many millions of instructions per second. The instructions take different amounts of time to execute. So there's no way to say that, oh, this is running X number of MIPS, because there's different instruction streams. I've understood that IBM in 1972 introduced the System 370-158, and they saw that they got a 1 MIPS processor, and they were very excited until they ran TSO on the machine and realized TSO was not generating 1 million instructions per second. So different instruction streams will give you different rates of instructions per second. But this MIPS today really is, again, just a relative measure of capacity. And we're going to talk about all these relative measures of capacity and where they derive from on the next slide. Know, though, that the MIPS ratings are provided from multiple sources. Okay, so there's Gartner, there's Cheryl Watson, produces a more nuanced table than Gartner, for example. Other consultants and products may have MIPS ratings as well. You can go generate your own from the LSPR data if you prefer. Although in reality, if you're trying to compare machines across different generations, the correct answer is to use IBM's free ZPCR tool to do that. Okay. And then finally, of course, IBM provides something called PCI, or Processor Capacity Index, which is really just MIPS by any other name. So why don't they call it MIPS? Probably because they don't want to be dragged down into the software pricing discussions with the ISVs, because the ISVs often will use this capacity. They will write the contracts in terms of MIPS. Unfortunately, there are multiple MIPS charts available. And so when somebody came and asked me, how many MIPS do we have on the floor? I always knew that that was because they were investigating a new piece of software or an upgrade to a piece of software and needed to know the capacity on the floor. And so my first answer was, what software are we talking about, so we can understand what the contract says in terms of whose MIPS rating we should really be using. Note that IBM speakers will often even refer to PCI as MIPS. I try to use the term PCI so you understand the origin, but I will probably fail and call the IBM PCI MIPS as well. Although, again, in this context, PCI and MIPS you can basically think of as the same relative comparison of capacity that's on a very similar scale to each other. So all of these measurements, the service units per second, the MSUs, and the MIPS are what we sometimes call single number metrics. In other words, it's a single number to represent the capacity of the machine. These are all derived from something called the large system performance reference, whereas large system is IBM speak for mainframe. And this is a set of workloads that are run by IBM in a test environment, and they run the same workload on, for example, configuration A and configuration B. Okay. And if you find machine B can process twice as many transactions per second as machine A, well, then they say, well, if machine A was 200 MIPS and B is processing twice as much work per unit of time, then B must be 400 MIPS. Okay. And that's exactly the way it's done. Everything is relative. So you compare how much throughput you can get out of one machine to how much throughput you can get out of the another machine. You said, oh, well, we used to call that older machine capacity X. We apply the ratio of the throughput to X, and now we get a new capacity Y for the new machine. Okay. Now, not every configuration is tested. These machines literally have hundreds of configurations, so the results are interpolated. And also notice that it's a particular configuration of workloads and LPARs, right? This configuration of particular work and LPAR will be different for you. Okay, so understand that this is a test thing. Everything is relative. And your exact results will vary. So these couple of charts are just to point out, to help make the point that the even though, because these are all sourced, the service units per second, the MSUs and the MIPS or the PCI are all sourced from the same test, they all should follow the same pattern. And in fact, they do. This is PCI per MIPS per MSU, basically. And if you look at that for the different machines over the last several machine generations, you look that those lines all follow the same basic trend here. Now there is variation, right, in terms of how many CPs and which speed generation you have, but you can see that this relative ratio stays more or less the same. So in other words, if you had an MSU rating for a machine and you wanted to figure out how many MIPS it was, if you multiplied it by, well, somewhere between 8.1 and 8.5 on the very high end up here, maybe more accurately somewhere between 8.1 and 8.3 for most customers, right? You'd be in the right ballpark for the number of MIPS. Similarly, if we look at the service units per second per MIPS, if you took a look at your service units per second and you divided it by, somewhere in the order of a little over 52. If you're out here on the larger machines, maybe it's a little less than 51, but you can do that division and you get something pretty close to what that table lookup said, right? So now this may look like, well, there's quite a bit of variation from the low end to the high end here, Scott. Well, it only looks like that because we didn't make those charts zero based. If we actually start those y-axes at 0, you'll see that they're pretty much solid across here, right? The variation from in that ratio from here to here is actually not that great, right? It's relatively small. So what are these different measurements good for? Well, we have them for different purposes. First of all, service units, we use WLM and SRM used to measure the workloads, and they're recorded in the SMF measurements. MSUs are a capacity rating. They're primarily used for IBM MLC pricing, also for IBM, often at times for IBM ZOTC or ZIPLA pricing as well, although that's a little bit indirect because those things are often priced in value units, which then often gets converted to MSUs in terms of actual capacity. And then, as I said, MIPS are most often used for ISV pricing. Notice if you're doing these for software pricing purposes, you do have to go look up the values. Don't just do the calculation off from service units per second, because you might want a little more accuracy in terms of agreement with what your vendor thinks the machines are, right? And all of them is because, you know, perhaps your manager just insists on seeing a report in MIPS or MSUs. And they all approximate an estimate of machine capacity relative to other machines. Again, I must stress that if you are doing capacity planning, you're planning an upgrade from machine A to machine B, please use zPCR, input your LPAR configuration to get a better understanding, a more accurate understanding of what the relative change is. zPCR is also based on the LSPR numbers, but zPCR takes into account your actual LPAR configurations and basically will skew those LSPR ratios to better match what it expects your particular configuration to behave like. Now those are okay, but I like more concrete measurements. We talked about CPU time. That's nice and easy. Physical utilization percent is also good for me. That's, you know, things like your KEC utilization. How much of the KEC overall did I use? APPL percent is basically a percent of one CP that a workload is using. Percent of one CP, percent of the overall machine, number of CPs used. All of those are things that I can pretty much hang my hat on and remember that, okay, if this particular workload is using 1.5 CPs worth of capacity, I probably have a pretty good understanding what that means in my environment, right? Because I can probably understand, well, first of all, understand that, hey, that's 1.5 CPs, so this workload has more than one work unit running, right? So that we can actually get more than one CP's worth of capacity consumed. But for me, they're much more intuitive than trying to calculate these things in MIPS. So if you have some measurements in SMF data, they're recorded in service units, though. Note that you can work backwards from service units to get to CPU time. Physical utilization is just CPU time divided by interval time. So in other words, if we consume 300 CPU seconds in a 900-second interval, then that's 33.3 APPL percent, or basically 1/3 of a single CP, right? So that's easy math to do. And then for a percent of the total KEC, we can just take the recorded CPU time and divide it into the interval time times the number of CPs. So if an LPAR used 1200 CPU seconds and there was three physical CPs on that machine, then 1200 divided by 900 times 3 is 44.4% of the total machine. Now, if your manager wants that in MIPS or MSUs, we'll multiply the percent of the total KEC by the MIPS or MSU rating of the machine. So in other words, in this example here, where the LPAR was 44% of the machine, if that particular machine was rated at 929 PCI or 116 MSUs, just do the math, and there's the capacity consumed in MIPS and MSUs. So this chart I stole from my colleague Peter Enrico because it's a great chart and I cannot do better in terms of explaining where these the LPAR, the CPU time breaks down. So this just kind of shows that you have a total physical utilization of the KEK up here at the top. That's made of multiple LPARs, right, running on that machine. So each LPAR has this total LPAR dispatch time. There's also a little bit over here on the right called physical. And what physical is Prism managing the LPARs, okay? There's also a little bit of partition LPAR management time within each LPAR as well. So that's recorded by LPAR. This physical over here is across all LPARs. It's Prism doing the larger management across all the LPARs. Within the LPAR, individual LPAR, if you subtract off the management time, and I should point out here that the management time slice and this physical time slice here is grossly oversized on this. This is not to scale. These should be very tiny slices. What's left over is the effective LPAR dispatch time. And then within the effective LPAR dispatch time, we have both what we call captured and uncaptured. And captured time being basically the time that we can accumulate to the workloads of service classes, the service class periods on the SMF72 records, okay? And then down here we have, of course, the individual address spaces or enclaves. Note that there is uncaptured time within a given LPAR because there's time spent by the operating system doing work on behalf of all the work on the LPARs, right? Or all the work on that particular LPAR. So where do you get these values from? Basically, the type 70s record the LPAR level data up here like we talked about before. The type 72s give you this view down here, and then the type 30s go down to the address space level. Now you can do the calculation for captured time and uncaptured time both on a type 30 basis or a type 72 basis. We most often then do it on the type 72 basis though. So this example here is we just take the total LPAR dispatch time. We can convert it then to the KEK utilization, transferred to physical utilization percent. This makes it very easy to see that this particular machine was basically maxed out here for this period of time, right? It was running at 100% utilization, okay? That's actually what the little red bars down here are indicating, hey, that's getting pretty busy. You might want to pay attention to that. Notice too, though, that this orange physical here is a very tiny little time slice here. And that's as we would expect. And so we can do some calculations here, right, to say if this particular LPAR used 20% of the machine, what was its dispatch time? We can go do the math, and it all works pretty easily, right? So what happens if your manager wants MIPS instead of percent utilization? Well, you can take a sticky note and then put it over the y-axis there, and now you have MIPS, right? Because this was the total capacity of the machine. This was my 100% mark. There you go. Now it's in MIPS. So while I don't expect you to actually do that, you get the point here that this conversion is very straightforward. This also tries to point out too, or this is where I point out that if you're just doing this, for example, in Excel, be careful of Excel saying, oh, you know what, that y-axis should go to 10,000. And then it suddenly looks like the machine is not maxed out because the y-axis is 10,000 MIPS, and the MIPS loss, unless you know exactly how many MIPS that machine is, you've lost that context for how busy is the machine really? How much of my capacity am I really using? Yes, okay, fine. If I see it using, 8,000 MIPS here, I can say, well, it's using 8,000 MIPS, duh. But what's more important to me is, oh, well, that's like 82% of my machine. That's kind of a more interesting, a more concrete number for me. So these couple of slides just say if we're going to look at one particular interval from the RMF post-processor report, it's very nice that we look at this in graphical form. If you don't have such a tool to nicely show you this in graphical form over the course of the day, you always have the RMF partition data report or whatever the equivalent in CMF is. And this is what that report looks like for basically that interval of time, okay? So what you'll end up seeing here is here's my individual LPARs, here's how many CPs I had on the machine. Here's the total dispatch time, the total CPU time consumed by each individual LPAR, okay? And so if we add all of those up, we can do the math, and actually RMF very nicely does the math for you over here, so you can understand exactly what the utilization of the machine is. Obviously, this is a little harder to understand if we're only looking at one interval, so there's a lack of context, but you get the point here. Okay, so here we're focused on this one production LPAR. This one production LPAR consumes 79% of this 707. So this is a Z13 707. So 79% of 7 CPs is 5.53 CPUs worth of capacity. Okay. Now, if we look at that on an APPL percent across the service classes, you may notice that this is peaking out here as something like 5.4% of a CP. Remember, APPL percent is percent of an engine, okay? So if we have GCP APPL percent or Apple percent, this 5.4 represents that this LPAR consumed 5.4 CPUs worth of capacity. So why is there a difference there? Well, the difference there is the uncaptured time. Okay, so the time above this 5.4 that really should be peaking at 5.53 is that uncaptured time. So we calculate a capture ratio based on the captured time divided into the effective dispatch time. You can also calculate the uncaptured time as the effective dispatch time less the captured time. Your general target should be to see a capture ratio above 90%. But note that some uncaptured time is always normal, and you're always going to have some uncaptured time because zOS can't directly attribute some system-related work to specific workloads. Okay. This is just an example of how we show that. You can see in this particular case, this system prod AA here has a pretty much ideal capture ratio of almost always above 95%. That's great. That's not necessarily what you will always see, though. In fact, this study now goes back a couple of years. I need to redo this, but this was from several systems. I don't remember exactly how many, but I believe it was dozens of systems across multiple customers. And basically, what we've plotted here is their capture ratio on the y-axis over here versus the consumption of the LPAR and MSUs. So you can see as LPARs get busier and consume more MSUs, their capture ratio naturally appears to be higher. Why is that? Well, in general, probably because those LPARs are doing more work. That more work is probably, hopefully, more business work, not just more work of the system managing itself. Certainly, the system-related work goes up as well, but more work because more business work done is what we're hoping for, right? So the point of this chart was I just zoomed in now to less than 200 MSUs. And the point we can see here is that once you get down an LPAR that's down below something like 20 MSUs, it gets really hard to stay above 90%, right? Because there's, again, a certain amount of fixed overhead in the system that's just there to manage the system. You know, it's running the CPU chains, it's making sure everything gets dispatched appropriately, it's sampling all the work on the system. Even if there is no work on the system, there's still all of your monitors and all that sort of stuff that's running. So you will see that as you get to the relatively small, lightly loaded LPARs, your capture ratio will naturally go down. What this cluster is over here, I have no idea. This is some sort of anomaly that somebody should look at. Actually, pretty much all of these under 80%, I'm kind of interested in because you can see they're definitely an anomaly compared to the vast majority of the dots that are above that 85% line for sure, especially once you get above 40 MSUs. So evaluating capture ratios. If your capture ratio is above 90%, there's probably little you can do for tuning it. I mean, there may be some you can gain back occasionally, but it's probably not worth your time most days to go chasing after it. But if a capture ratio is regularly below 85% and that system is a significant contributor to your software costs, I would definitely look at it. You know, look for old traces or slip traps. In IEA opt, there's a parameter called RMP-TTOM. I call it rumpty-tum. This parameter here is basically influences how SRM manages a system, how often it goes through its housekeeping. We still run into customers that have this set at 1,000, and the default today should be at least 3,000. You can actually set it higher and gain back some responsiveness and improve potentially your capture ratio by setting it even higher than 3,000. In general, values up to 10,000 I'm usually pretty comfortable with, especially on the non-production systems, because basically it goes to saying how responsive SRM is to changing situations. If it's set to 1,000, you should absolutely, at the very least, remove that setting from your IEA opt to at least get the default. And like I said, you could consider changing it even higher. Look for paging activity, contention. Look for large SMS pools, which is one of the things we've been hearing over the last couple of years, is that allocation sometimes can influence this. But unfortunately, tracking down uncaptured time is sometimes difficult because, after all, it is uncaptured. Okay, so in the 13 minutes or so we have left here, we're just going to finish out with some discussion of zips. Zips always run at full speed. So if you have a subcapacity machine where the general purpose engines run less than quote unquote full speed or full capacity, then understand that the zips are running at a larger capacity. They're getting more work done per unit of time versus your general purpose engine. And there is a normalization factor in the data. It's actually in multiple places. This one field is just one of the places it is. And this is used to provide a conversion factor between the zips and the general purpose engines. Okay, so you basically multiply by that field and divide by 256 to get the general purpose engine equivalent time for the raw time that was consumed on the zip. Okay, this normalization factor comes from the service units per second ratings, and it's the ratio of the service units per second of the single CP subcapacity models and full capacity models. In other words, if you're on a P02 here, a 2965 P02, the normalization factor is a ratio of P01 to a Z01 for a 2965. Okay. You may also see, you can look at the processor speed and cycles per microsecond from the SMF113 data. You'll notice that this ratio will not exactly match this ratio, and that is expected. Just comparing the cycle times does not really exactly match up to what you expect in terms of getting work done, which is what this is trying to understand, because again, it's derived from the LSPR ratio, which actually measures work getting done. So just to point out here, there were 2 zips on this machine. The peak utilization across those 2 zips is about 12.6% of the machine. So this would equate to about a quarter of a single zip's worth of capacity. Okay. And in fact, if we take a look at that utilization by service classes here, we'll see that it comes out pretty close to a quarter of 1 zip's worth of capacity. Now this is APPL percent for a zip, so it's percent of a zip. Now this is zip APPL percent, so it's the raw zip time. It's not converted to general purpose engines. It's also not adjusted for SMT, which again is a whole different discussion I'm not going to get into. But the one thing I do want to point out is note that this 25% is very, very close to our calculated value of 25.2% over here. And that's expected. If you look at a capture ratio for zips versus general purpose engines, you'll find the capture ratio for zips is much higher because there's not the system overhead work being done on the zips that there is on the general purpose engines. Now, we can convert that zip APPL percent to zip APPL percent GCP, meaning this is now adjusted to percent of a general purpose engine. Okay, and you'll notice that now we're consuming about 75% of a general purpose engine. This was actually zip, it ran on the zip, but if all of that work had run on a general purpose engine because we had no zip, then we would have consumed 3/4 of a general purpose engine, which is as expected because zips run faster than the general purpose engines on subcapacity machines. So this chart just says that, we've been talking about physical measurements that come from direct measurement of CPU time. CPU time is a physical measurement, even though you're running on a logical CP on the LPAR. Remember that CP the physical CP that the logical CP is running on can't be running work for multiple logicals at the same time. So even though it's a logical CP on the LPAR, the CPU measurement is a physical measurement of capacity, okay? And just to point out that Prism time slicing is responsible for dispatching the logical CPs to physical CPs, and zOS is responsible for dispatching the logical CPs to workloads. Now, sometimes we may want to look at things in terms of logical CPs, which is primarily done to understand how much of our logical capacity we're using. In other words, if I have an LPAR that has 3 CPs assigned to it on a 5-way machine, am I using all 3 CPs worth of that capacity? Because assuming I have weights set appropriately and all that sort of stuff, I could consume up to 3 physical CPs worth of capacity because I have 3 logical CPs. So a logical utilization helps me understand how much of that logical capacity that I have that I'm consuming. Personally, I'm not going to really get into this, and personally, I don't like the logical measurements quite as much because then I have to get it back to how much of my total capacity am I actually using. I have to go back and understand how many logical CPs do I have relative to my physical CPs. So the logical measurements in most cases today, I don't care as much about. And the reason I don't care as much about them is because in most configurations, we have LPARs with one or two more logical CPs than they really need. Those low pool CPs are parked by hyperdispatch, and so they don't provide the same overhead that they had in the old days. In the old days, we tried to manage the number of logicals very, very closely. It's a little less important to do that today. So today, that logical measurement's a little less important. Okay, in the final couple of minutes here, how many MIPS is that batch job? Is a question that we get asked sometimes, and the answer is easy to calculate, but it depends on the time frame you want to consider, right? So do you want to consider how much capacity was consumed over the duration of the batch job, over the duration of the RMF interval or the SMF type 30 interval, over the duration of the hour or the duration of the day? I've seen people do all of these, okay? I don't necessarily agree with all of them, but I've seen people do all of these or want to do all of these, right? And obviously that will change your calculation because it's changing the amount of time that you're dividing into. So I'm not going to read all of this. You can read this later. The idea here is that, we have a batch job that starts in the middle of an interval, it crosses over the interval. So there's multiple ways that we can take a look at this batch job and say, well, what percent of our capacity did we consume relative to the interval we're interested in, right? And, assuming this is a 5-way machine at 840 MIPS, over the course of the batch job, we could say we consumed 84 MIPS, right? You have to be careful when you start doing things like over the course of the batch job, because then the tendency is to add up all my batch jobs, but all those batch jobs didn't run simultaneously, so you can't just add them up easily, and there's opportunity for you to lose sight of the context. So in summary, so I can go look and see if we have any questions. The CPU time consumed is the basis for understanding how much of your CPU capacity is consumed. And CPU capacity for a given machine can be described via these various CPU metrics such as service units per second, MSUs, MIPS, and PCI, all of which are the single number metrics that derive from the LSPR test. And converting from CPU time to those other metrics is really a point of multiplying the percent of the total capacity consumed by the specific capacity rating. And the capacity consumed depends on the CPU time consumed during the specific interval you're concerned with. The same CPU time over a larger interval, such as in the case of our batch job, comparing it over the course of a day as opposed to the course of the batch job, means you used a lower percentage of the total capacity. All the math is pretty simple though, okay? So don't forget to submit your session feedback. Here's a link, I believe, yes, they're in the chat. Thank you very much. Here's a reminder about the charities as well. So thank you all for attending. I do appreciate it. I would appreciate it as well if you provide feedback. That's always appreciated. And I have a couple of minutes left, so that was intentional so I could get to a couple of questions. I'm not seeing any at the moment. Did I miss any here?
No questions have come in at the moment. Just a reminder, if you want to ask questions, feel free to type in the chat box. Or if you rather prefer to speak, then I can unmute you as well. Just let me know.
Sounds great. I do, again, appreciate everybody coming today. Hopefully next year we can get to this maybe in person.
Yep, I don't think we've got any questions coming through just now, but can people contact you as well, Scott?
Yes, absolutely. So let me go throw my beginning slide back up here. So there's my email address. It's pretty easy, scott.chapman@epstrategies.com. Feel free to email me. Always happy to discuss zOS performance topics for sure.
Perfect. Well, thank you so much, Scott. Really appreciate your time, and thank you for everyone that attended. Again, yeah, would really appreciate the feedback, and of course, any donations as well to NHS Charities Together will be much appreciated also. And with that said, thank you so much, and I hope you all have an enjoyable rest of the day.
Okay, thank you very much. Have a great day, everybody.